Welcome to the Deep Dive. We're the show that really tries to cut through the noise and get to the core insights from, the cutting edge. Today, we're tackling something pretty fascinating. It's a challenge maybe many of you have felt if you're trying to build something new. How do you actually bridge that gap? That gap between an abstract idea, something just in your head like a design intent, and making it, well, real, physical,
Yeah.
tangible. This deep dive is maybe a shortcut to understanding a really revolutionary approach to figuring that out. We're immersing ourselves in what our sources call the Topy Framework. It's described as this powerful, formal method for translating what we want into basically how we make it. It's about giving a precise shape, almost a mathematical one, to our intentions so they're ready for the real world.
And what's really exciting here, I think, is that this isn't just theory. It's not just talk. This framework, it sits right at this amazing crossroads. You've got algebraic, topology, beautiful, abstract math meeting, practical electrical engineering, and even computer architecture. It's all pushing towards something really ambitious, like a topological processing unit, a TPU. It's a machine designed specifically to bring these abstract ideas into physical reality. We're really talking about laying the groundwork for building things in a new way.
Okay, so let's explore that vision a bit more. The core idea, the ambition, is to actually design the architecture for this TPU, something that takes that abstract framework and just translates it directly into a working physical model.
Right. And from an engineering standpoint, it's a classic strategy for tackling a really deep problem. You break it down, decompose it into these distinct, manageable subsystems. Each one can be optimized on its own, but they have to interact seamlessly, right? Through really well-defined interfaces. That structured breakdown is what makes something this ambitious actually achievable. It moves it from just a concept to something you can, construct.
So to make this happen, our sources point to four key components. They make up what's called a physical Topy kernel. You can sort of imagine them as a specialized team. Each member has a very specific job, but they have to work together perfectly. First, there's the Speculative Prediction Unit, the SPU. Think of this as the system's draft model. Its main job is speed. It rapidly predicts what will happen if you apply a certain operator, like an action, to the system's current state or pattern. It needs to predict the resulting pattern, P plus delta P, really fast. And it's often built using things like machine learning accelerators, maybe DSP blocks on an FPGA, optimized for raw prediction speed. Kind of like speculative decoding in LLMs, Get a prediction out fast, even if there's a tiny trade-off in perfect accuracy at first. Speed is the priority there. Okay, the next up is the Verification Constraint Unit, the VCU. This one's the target model. It's the gatekeeper.
Exactly. It's crucial.
It rigorously checks the SPU's prediction that predicted change. Delta, against a set of hard rules. Constraints, things like, say, maximum power limits, or just checking if the proposed change is even physically possible for the system.
And our sources mention using FPGA logic fabric for this. You get nanosecond level latency for verification. Its whole reason for being is deterministic timing and absolute reliability. It cannot fail. If a prediction breaks a rule, the VCU stops it right there.
Right. Then you've got the Physical Realization Unit, the PRU. This is the actuator. This is the part that actually does something in the real world. It takes that transformation, once it's been verified by the VCU, and applies it.
Yeah, it manipulates some kind of physical carrier. Could be a light wave, could be an RF signal. It physically reshapes that carrier based on the validated plan.
And the tech behind it.
Yeah.
Often things like programmable analog hardware, maybe spatial light modulators if you're working with light, or software-defined radios for RF signals. The PRU needs to be optimized for fidelity, how accurately it makes the change in range, like how broad a set of operations it can actually perform.
Makes sense.
And finally, number 4, the State Measurement Unit, the SMU. This is your sensor array. It's constantly watching, measuring the current physical state of the system.
Right. It needs to know what's actually happening right now.
It generates what's called a homological pattern, P, from that physical carrier. Think of it like a simplified fingerprint of the system's essential shape or structure.
Even if the exact physical details change, that underlying pattern might stay the same.
Yeah, and it uses things like detector arrays, high-speed ADCs,
Yeah.
CMOS or CCD sensors for light, or the ADC in an SDR for radio. And obviously, the SNU has to be optimized for precision and bandwidth. It needs accurate measurements, fast enough for real-time feedback.
So the real magic, the ingenuity, is how these 4 units work together. They form this continuous control loop. The system is constantly self-aware in a way. It
Yeah.
measures its state with the SMU.
Yeah.
The SPU speculates on the next action.
Predicts the outcome.
The VCU verifies that prediction against the rules.
Checks it.
And then the PRU acts on it, changes the physical system. And this just keeps going. It's a constant feedback cycle that actively maintains a desired state, or maybe steers the system towards a new one, a specific homological state. This whole dance, this interplay, that is the physical implementation of the execute function. It's how abstract intent physically happens.
Okay, so we have this elegant framework, this team you described. But how do you test it? How do you go from this, sophisticated theory to the very first actual experiment?
Our sources talk about defining a minimum viable experiment, an MVE, and the one they picked to start with is called spectral hole punching. They suggest using software-defined radio SDR, mainly because it's accessible, flexible, a good starting point.
Exactly. For this MVE, the homological pattern is pretty straightforward. It's just the power spectrum of a radio signal. And the topological feature we care about is a hole in that spectrum, a null, a frequency where the signal strength drops way down.
Okay.
The number of those holes, or maybe how deep they are, that's analogous to what topologists call Betty numbers. It's like count to the features. So the pattern is the spectrum, the feature is the hole.
Right. And the topological operator O is super simple. Punch a hole at frequency F, just make a null at a specific spot. So the process looks like this. The SMU measures the current spectrum, P. The SPU predicts what the spectrum P will look like with a deeper hole at F. Then the VCU checks that prediction, like, does it violate constraints? A common one might be no overall amplification beyond 0 dB. Can't just boost the whole signal.
Right, just make the hole.
Exactly. And if the VCU says, okay, the PRU applies a notch filter, a specific type of filter, to the live radio signal at frequency F.
So practically speaking, how would you run this test? You'd maybe generate a test signal first, like white noise, but maybe add a strong interfering signal at some frequency, phi.
Yep, that's a good way.
Then you issue the command, punch hole at phi, and the system just starts its loop.
Yeah.
SPU predicts, VCU verifies, PRU applies the filter.
And then the SMU measures the new spectrum, and you watch.
Success is pretty obvious then. You see a big dip, a null, right at phi. And the system doesn't go crazy, it stays stable.
Precisely. A clear result. And this brings up a really important engineering point, balancing the speeds. Each unit has its own processing time. You have to benchmark them individually. Maybe the SMU takes 1 millisecond to get a spectrum reading. The SPU is super fast, maybe 0.1 meters. The VCU is even faster on FPGA, say 0.01 meters. But then the PRU, actually reconfiguring that analog filter in the SDR, that might take 2 milliseconds.
So the PRU is the bottleneck there.
Exactly. It's the slowest member of the team at 2 meters in this example. So that sets the pace for the entire loop. Your overall system control loop bandwidth is limited to 1 divided by 2 milliseconds, which is 500 hertz. It really shows how you optimize each function as much as possible, but the team's overall speed is governed by the slowest link, often a physical limitation. That really dictates your system design.
So, okay, this first hole punching experiment, it's more than just a cool demo. It gives you a clear pass-fail. It sets baseline performance numbers for each of the 4 units. And most importantly, it proves the whole concept works, that speculate-verify-realize loop. It validates the core idea. Now you might be listening and thinking, okay, this Topy framework sounds powerful, but wait, if you need a Topy model scanner to build and understand the thing, how do you even start? It sounds like a classic chicken-egg problem, doesn't it?
It does, and that's not a flaw, really. It just shows how new this research area is. But the sources outline a really clever way around it, an iterative bootstrapping strategy.
Bootstrapping. Okay, how does that work?
It unfolds in basically 3 phases. Phase 1 is all software simulation. You build a virtual model, a digital twin of everything. The SPU, VCU, PRU, SMU, all modeled in software like Python or MATLAB. This lets you iterate incredibly quickly, test limits, refine your algorithms. There's 0 hardware cost, massive flexibility. It's where you sculpt the initial design.
Okay, virtual first. Makes sense.
Then, phase 2, hardware in the loop, or HIL. This is the crucial bridge to reality. You keep the complex brains, the SPU and VCU algorithms running in software on a powerful computer, but you connect that computer to actual, simple, maybe off-the-shelf hardware, like an SDR to handle the physical realization, PRU, and the measurement, SMU.
So part simulation, part real hardware.
Exactly. This phase forces you to deal with the quirks and limitations of real hardware. You get invaluable experimental data that feeds back into refining your software models.
Okay, bridging the gap. Then phase 3.
Phase 3 is the integrated prototype. This is where you take all that intelligence, the refined algorithms for SPU, VCU, the control logic, and you migrate it off the host computer. You put it onto dedicated embedded hardware. Usually an FPGA is the target platform here. And at that point, you've built your first generation, probably application-specific Topy processing unit. It might be specialized, might have limits, but it is the physical framework built step by step.
And what's really cool about this staged approach is what the sources call a recursive payoff. It sounds like each generation of the scanner helps you build the next, more powerful one.
That's exactly it. Your flexible software simulation helps you design the HIL prototype. The HIL system gives you the practical know-how to build a fully integrated RF scanner, maybe using that SDR knowledge. And then that experience with RF, understanding how to manipulate its topological patterns, gives you insights that accelerate building, say, an integrated optical scanner later on.
So you're literally using the tool to build better versions of the tool, like climbing a ladder where each rung helps you build the next one higher.
Precisely. It's a very powerful development cycle.
Now, the technical side is obviously impressive, but our sources also spend time on something else, something they call the poetry of the project. It sounds like there's an artistic or philosophical dimension here, too.
Oh, absolutely. And it's not just, window dressing. It seems to be a really core part of the motivation, a guiding principle. There's this poetry of mirroring they talk about, how an abstract intent, something purely conceptual, gets reflected almost perfectly down through the layers, from algebra to software code to the electronics, and finally into physical manipulation. It's like a recursive chain where the abstract becomes concrete but keeps its essential form.
A clean translation.
Yeah. And then there's the poetry of the loop, that execute cycle, SPU, ECU, PRU, SMU. It's like an Ouroboros, the snake eating its tail. The system is constantly sensing itself and modifying its own topology. It suggests this kind of mathematical self-awareness, an active engagement with its own structure.
Wow.
And maybe the deepest layer is the poetry of realization. That word realize, it has that dual meaning, right? To understand something deeply.
And to make it real, to bring it into existence.
Exactly. And this whole project seems to be about embodying that duality, showing how deep understanding allows you to actually create that poetic quality, that resonance. It acts like a compass. It's a huge motivator. It turns it from just building a tool into something more like conducting a symphony between thought and reality.
That idea of realization is both understanding and creating.
Yeah.
That really feels like the heart of it. It elevates the whole thing. Okay, so let's scale up from that first SDR experiment. Imagine extending it. What happens if you start using multiple detectors, pluralizing them, or increasing the distances between them, or even putting them in different kinds of physical environments, different terrains?
Yeah, that's where the power really starts to compound. The power of plurality, using multiple detectors, gives you things like synthetic aperture, like using multiple small telescopes together to act like one giant one, giving you much higher resolution. It also gives you multi-perspective validation, different viewpoints confirming the same pattern. And crucially, it lets higher-order homological patterns emerge, patterns that only exist because of the relationships between the different nodes in the network.
Okay, so more detectors mean richer information. What about distance?
The power of distance lets you systematically probe topological features at different scales. Some things might only become apparent over larger separations. It also forces your model to incorporate new physics, maybe signal propagation effects, or interactions that weren't relevant when everything was close together.
New terrain, different environments.
The power of terrain is about stress testing the whole framework. How general is it? How robust? Putting it in diverse environments, cluttered urban canyons, open fields, underwater, challenges it with a much richer, more complex universe of patterns and physical conditions it has to handle.
It sounds like we're moving beyond just measuring along a line with multiple sources, positioned strategically. Could you start to define and interact with the whole volume?
Absolutely. That's the next big leap. You go from understanding a surface or a line to defining and manipulating a volume. This opens the door to modeling and realizing complex volumetric patterns. You could potentially do things like tomographic reconstruction, mapping out the inside of something invisible based on how signals pass through it.
And the actions you can take, the operators, they become more complex too.
For sure. You'd move beyond just punch hole to things like op-stretch, to deform a volume, op-twist, to rotate its internal structure, or a puncture to create new internal holes or boundaries. And at this stage, the network itself becomes the carrier. The physical arrangement of your detectors, their geometry, is the primary structure, the fabric on which you're performing these topological surgeries.
When you give an example.
Sure. Imagine a tetrahedral spectrometer. You place 4 synchronized SDRs at the corners of a tetrahedron. You could use this setup to characterize and then actively manipulate a whole 3-dimensional radio field within that volume, shaping it in complex ways.
This is getting really advanced, which leads to maybe a very technical, but apparently very powerful question that comes up in the sources. Can we use something called integral Fourier duality to simplify the connection between Hodge theory, which deals with continuous shapes, and Topy's realization functor, which builds discrete structures? And just to remind listeners that realization functor ROP is essentially the mathematical instruction set for how to physically build something based on its abstract spec.
Yes, absolutely yes. The sources are really emphatic about this. It's presented as a profound simplification, a major breakthrough. It essentially reframes the whole problem in this incredibly elegant mathematical language. It builds a bridge between the continuous world of Hodge theory, think differential forms, complex cohomology, tools for understanding smooth shapes globally, and the discrete world of Topy, which works with building blocks, combinatorial structures, homology groups for counting discrete holes and connections.
Okay, so it connects the smooth and the discrete. How does Fourier duality do that?
Integral Fourier duality, sometimes called Pontryagin duality, acts like a Rosetta Stone. That's the analogy used. It translates the continuous forms from Hodge theory into specific, discrete sets of numbers, integral Fourier coefficients, or periods. These periods then directly tell you about the Topy patterns, the Betty numbers, the torsion, the stuff Topy cares about. So the realization functor, ROP, is now guided by these concrete Fourier coefficients. They act like a blueprint for how to modify the geometry. For example, a specific period value associated with a loop might tell the ROP exactly how to attach a new handle or cell to achieve that value. Philosophically, it's a shift from just analyzing global properties, Hodge, to being able to do precise, local, combinatorial construction.
Well, the sources really emphasize this connection as kind of, well, newsworthy. Why is bridging Hodge and Topy considered such a big deal? Why does it bring, as they say, kudos?
It's considered revolutionary for a couple of key reasons. First, it solves a deep communication problem. It creates this canonical, mathematically solid dictionary between continuous analysis and discrete synthesis. That's huge. But maybe even more dramatically, it transforms an abstract proof into a constructive algorithm. The Hodge conjecture, right? One of the biggest unsolved problems in math, a Millennium Prize problem. It's fundamentally an existence question. Does a certain kind of geometric structure exist for any given algebraic specification? This connection shifts it. It turns it into a construction problem. Okay, how can we build it? Can we algorithmically find or construct that geometry? That's a massive paradigm shift for mathematics itself.
Wow, okay, turning existence into construction.
Yeah, and it definitely has that wow factor because it connects this incredibly abstract math to things we can relate to, like digital audio sampling or how MRI machines reconstruct images from frequency data. It's about taking one of the deepest questions in pure math and reframing it as a problem of essentially programmable matter. Can we program reality at this fundamental level?
Okay, let's take this incredibly powerful lens now, this Topy-Hodge connection, and turn it towards some really complex scientific frontiers, like quantum electronics or even string theory.
Right. For quantum electronics, imagine applying this framework. It could totally redefine how research is done. Instead of just tweaking knobs on equipment, parameters become these rich algebraic specifications. You could specify, say, I want a quantum system with this exact topological order, or I need this precise value of conductance quantization.
You specify the desired quantum property directly.
Exactly. And the whole research process becomes a formal loop. Speculate, propose a structure, verify, check against quantum mechanics rules, realize, try to build it. This forces us to ask deeper questions like, are our current quantum descriptions even complete? What are the absolute limits of what properties we can physically engineer into a quantum system? A concrete example, designing a topological qubit. You'd specify its required topological invariance, the mathematical properties that make it robust, and the framework would aim to output a physical recipe, a blueprint for building it.
Okay, that's quantum electronics. What about something as theoretical as string theory? How could this apply there?
Well, string theory has this infamous landscape problem, right? The theory seems to allow for a mind-boggling number, maybe 10 to the 500, of possible universes, each with different physical laws. How do we find our specific universe in that? We can frame this as a Topy realizability problem. Our universe's standard model, all its particles, forces, symmetries, becomes the homological pattern we observe.
The target pattern.
The target pattern. The huge question is this specific pattern P realizable as a stable vacuum state, typically associated with a specific geometric shape called a Calabi-Yau manifold X, within the rules of string theory? This reframes the overwhelming landscape into a more structured library of potentially realizable universes. We're looking for the book that matches our observations. Manipulating the VOP, the verification operator, becomes a way to rigorously test string theory's fundamental axioms. Can they actually produce our universe? The functor, which translates between descriptions, could potentially shrink that vast landscape dramatically by identifying equivalent solutions. And the ROP, the realization functor, represents the ultimate goal. Could we algorithmically derive the specific geometry of our universe, the Calabi-Yau manifold, directly from its abstract specification, the standard model pattern?
So the insight here is really profound. It's suggesting this isn't just a new tool, it's a whole new way of doing fundamental physics. A shift maybe from reductionism, just breaking things down, to realizationism, specifying and building.
Exactly. From just describing the geometry we see to using algebra to specify the geometry we want, and moving from simply making predictions to having a framework for rigorous, verifiable validation and construction.
Okay, after exploring these absolutely huge ideas, quantum systems, the structure of the universe, you might be listening and thinking, this is incredible, but where on earth do you actually start? How do you take the first practical step? Our sources propose a very feasible proof of concept, a POC, to demonstrate this whole paradigm shift in action.
Yes, and it's deliberately kept simple to be manageable, but it tests all the core ideas. For this foundational POC, you start with a very basic toy universe, just a single quantum particle that's constrained to move only on a circle.
Okay, simple setup.
The intent, P, is defined algebraically. You specify a desired energy spectrum. For example, you might say, I want a system that has exactly 2 ground states with the same lowest energy level, what physicists call degenerate ground states. The geometric realization X you're looking for is the potential energy function, Vx, around that circle. That potential is what dictates the particle's energy levels.
So the challenge is, can you use the abstract specification, the desired energy spectrum, to figure out the concrete potential function Vx that produces it?
That's the core POC challenge. And you'd implement it using software. You'd have software classes to represent that algebraic specification P. You'd have a VOP function that checks if a proposed potential Vx is consistent with the rules of quantum mechanics. And you'd have an op function that uses computational methods, maybe optimization algorithms, maybe searching a pre-computed library of potentials to find a Vx that actually produces the target spectrum P.
And what would you demonstrate with this POC?
You could show several key things. 1, unique realization. Take a known potential, calculate its spectrum, then feed that spectrum back in as the intent P and show that the ROP correctly reconstructs the original potential. 2, classification. You could provide a more generic specification, like 2 degenerate ground states, and show that the ROP finds a whole family of different potential functions Vx that all satisfy that condition. And 3, really importantly, falsification. You could feed it an impossible specification, maybe something that violates fundamental quantum principles, and show that the framework correctly identifies it as unrealizable. The VOP would fail it.
So even the simple particle on a circle example, it really tests all the pieces. The specification, the verification against physical laws, the realization or reconstruction. It provides that crucial groundwork, builds credibility, and shows this isn't just abstract theory. It's an actionable approach you can actually build and test, ready to scale up later. We've covered a lot of ground today, from the practicalities of, punching holes in radio signals through that elegant iterative bootstrapping, all the way to these really profound ideas about quantum mechanics, string theory, and the very nature of realization. What seems to connect it all is this incredible power, this beauty almost, in being able to formally specify what you intend to create. It's been a fantastic deep dive.
It really has. And you've witnessed how digging into these topological principles, this way of thinking, can fundamentally transform how we approach design, how we approach discovery, maybe even how we think about reality itself. So the question I guess we leave you with is, what abstract idea, what desired outcome that you have, are you now maybe inspired to think about specifying formally, and then perhaps figuring out how to realize?
A great thought to end on. Thank you for joining us on this deep dive. We'll connect with you again next time.